Alright, grade 12 chemistry. We're into unit 3, which is thermochemistry. This is all about how fast reactions happen and what we can change about reaction conditions to make things go faster or slower or give us the right products. So this is an introduction. We're going to talk about some basic physics concepts that are going to help us out. In particular, the kinetic molecular theory of reactions, the Boltzman distribution, the laws of thermodynamics, and then we'll talk about how we actually write energy into our chemical reactions, so that we know how much energy comes out when we do a chemical reaction. So that's basically what we're going to do during the day, so same kind of thing. Yeah, it's really a fundamental lecture that we're going to use a lot of these concepts over the next 6 videos that we're going to do. Let's just jump right into it with kinetic molecular theory, but before we do, a little background info and a little analogy for distributions and cutoffs. Here, for example, is the distribution of male and female heights. We see here women and men. We see the distribution of heights, the median for women, 5'5", the median for men, 5'10". And you can see, on average, men are taller than women. There is overlap, though. There are, down here you have men that are shorter than the average and women that are taller than the average, so you can definitely have a man that's shorter than a woman and stuff like that. The crossover kind of happens down here, around 5'7" or so, something like that. So this tells you how popular each height is for women and for men. So to understand a distribution, you have to kind of have this intuition for it. Notice that the women, the peak is higher up, and the men it's further out. So that means that there's more variation in men's height than there is in women's height. And notice these tails, these big long tails, right? There's areas down here, like down here especially, where you're kind of likely to find women that are that high, but very unlikely to find men that are that tall. Right, somewhere around 4'10" or so. That's a very, very, very low chance for men, but there's still a significant chance for women. Same thing on this side, right? Up here around 6'4", 6'5". There are definitely women that are that tall, but they're very rare compared to men that are that tall. So understanding these kinds of distributions is very important. And the other thing about this is cutoffs. Let's imagine for a second that we had a roller coaster, right? And the roller coaster had a minimum height, as roller coasters often do. Right? This green bar might represent that minimum height. This green bar that I can drag around, right, represents the minimum height of our roller coaster. Let's say our minimum height was, about here, right? About here. What does that mean for the women and the men that can ride our roller coaster? Well, we see here that all the men that are taller than the green line, right, which is most of the men, if we look at the red area here. These guys, they can't ride it, but these guys all can. So most of the men can ride it, they're fine. But only a small percentage of the women can ride it. Meanwhile, these ladies back here can't ride the roller coaster. If the roller coaster was, say, average woman height, half of the women could ride it, and half of the women couldn't, but most of the men could, right? Let's say we went nuts and made a roller coaster that had a minimum height of 6 feet. Oh, let me grab that. There we go. Yeah, let's say we went nuts and had a roller coaster where the minimum height to ride it was 6 feet. Well, you still have a solid percentage of men that could ride it. Most of them couldn't, but some of them could. But basically no women would ever be on a roller coaster, right? So this is the concept of cutoffs. You can have a cutoff that's higher than the average, and then there's still people that can ride the roller coasters. Even some women, just a few women here, like this little tiny tail here, that are more than 6 feet tall. Of course, most roller coasters are somewhere down here, right? Maybe a 5-foot minimum height or something like that. And then most men and most women could ride it. But that kind of concept, this concept of distributions and cutoffs, is going to become very important when we talk about thermochemistry, because one of the big things in this unit is the effects of temperature on reaction rates. And we'll talk about that kind of thing. So where am I leading with this is collision theory. Collision theory Collision theory states that molecules will react, when the reaction will happen, when they hit each other, when two things are correct. They have to be the right orientation and they have to be the right energy. So the right orientation and enough energy. So if they move too slowly, they just kind of move away from each other. If they hit fast, they can interact now, right? They've passed what we call the Coulomb barrier and they're actually close enough to react. But if they hit them the wrong way, right? If they hit the wrong way here, right? See, like here, this is the carbon trying to steal an oxygen off of this nitrogen. If it's the oxygen that comes in and hits, well, the oxygen is not going to want to steal an oxygen, so it's the wrong orientation. But here, if the carbon comes in and hits this oxygen, and it's moving fast enough, then it can actually go. Right? The carbon has to hit the oxygen fast enough. This concept of the right orientation and having enough energy explains a lot of these factors that affect the rate of the reaction. And we can look at it in a different way here. Here's another diagram of it. Here's reaction we're trying to do, oxygen, ozone, and nitrogen oxide here. When they collide, the oxygen, if it comes in at a glancing blow like this, the oxygen will transfer to the nitrogen, leaving O2 behind. Right? But it has to be one of these end oxygens so that it can get ripped off the end. If it's the middle oxygen that comes in and hits, right? The middle oxygen that comes in and hits, there's no chance of it popping out because it's got the two oxygens on each side. It has to be this glancing blow, not a straight, not a direct blow. So that's the concept. And if the glancing blow is too low energy, right, they'll just kind of go past each other. There's not enough energy for the actual transfer to occur. So that is collision theory. That is the kinetic molecular theory of chemical reactions, the collision theory. It explains a lot. So I'm going to pause. I'm actually going to go to an example. Actually, no, I'm not going to do that yet. Next up is the Boltzman distribution. So I'm going to pause and go to the Boltzman distribution. So this is the Boltzman distribution, or the Maxwell-Boltzman distribution. It tells you how fast particles are moving based on what temperature it is. So here, for example, we see that same kind of, like, remember that human height distribution? Here we see a distribution of speed of the particle versus the number of molecules moving at that speed. Here's the average speed and the root mean square speed. So that tells us what the temperature is. But notice that a lot of particles are moving faster than that. Just like average male height is 5'10", but you can easily find people that are over 6 feet tall. And then you got like basketball players that are super, super tall. There's just not a lot of them. So we see that here too. We have an average temperature. We have a temperature which is the average speed, but there are definitely particles moving faster and particles moving slower than that average speed. Right? And as the temperature goes up, the blue distribution is 25 degrees Celsius, the brown is 625 degrees Celsius. The curve gets flatter but wider, kind of like the male versus female distribution. Right? So this is the particles at 25 degrees Celsius. This is the same particles but at 625 degrees Celsius. You can see that the average has moved up, but also there are now molecules way up here that are moving very, 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 very quickly that we wouldn't be able to find or be very hard to find in this distribution. So higher temperatures increase the speed of the particles. It also increases kind of the proportion of them that are moving faster than the average. It makes the tail much wider. Why do we care about this stuff? Well, it helps explain a lot of interesting things. For example, it explains why water can evaporate at room temperature. You ever spill water and it just slowly disappears? Well, that water is turning into a vapor. We know that it turns into a vapor at 100 degrees Celsius, right? So what's going on there if it's like 20 degrees in your room and the water's evaporating? Well, the average might be 20 degrees, right? The average speed is kind of here. But some of the water molecules are moving fast enough to turn into a gas. Some of the water molecules have enough energy to fly off and turn into vapor form. So, the average doesn't tell you the whole story. There are some particles that will have enough energy to collide and do a reaction according to collision theory, even though the average isn't there. Of course, if the average moves forward, you have more chance. So this is the kind of the roller coaster thing, right? Why I talked about the roller coaster. If we have a cutoff, right? Let's make a cutoff. Let's pretend that our reaction can only happen, when the molecules hit each other at 1,000 meters a second. Let's pretend that's if they hit each other at 1,000 meters a second, they can react. Well, most of them in brown or in blue won't react, but there's a proportion of them in the brown that will react, and a tiny, tiny bit of them in blue that will react. So we predict then that the reaction will go faster at a higher energy, at a higher temperature, with the brown reaction compared to the blue reaction, right? So same concept with when we have water that's evaporating at room temperature. The room temperature might have this distribution, and this might be the cutoff for the water actually evaporating, turning into a vapor, but there is a small amount of them that will. And that's why we see it slowly evaporating. And when it's hotter, it evaporates faster because this distribution will shift, right? We can actually shift that distribution forwards, and it's faster. So there's more of them that'll evaporate at any given time. I'm going to switch over to an applet that kind of does this visually. So I'm going to pause and switch over to that. So here's a cool PHET simulation about reactions and rates. You can find the link to this down below. Basically, there's this little plunger, right, that can shoot a ball. You see there that it's not reacting because I didn't shoot it hard enough. All right, I can reset it. I think I can reset it. Reset, yes. Right, and if I shoot it harder, boo, hey, we get a reaction. Right, and I actually go back and forth getting a reaction. And I can see the energy view, right? You can see the energy. Here's the energy hump that I have to get over. And if I pull back enough and I make enough energy, right? If I don't go all the way up the energy hump, there's no reaction. And if I reset, if I go past the energy hump, like that, now I get a reaction. Not only that, you can actually see an angled shot here if I shoot it at an angle. Right, it won't react until it bumps into it. At least I hope not. There we go. Okay, but that was a glancing blow. It didn't react. So that's kind of cool. Hopefully it'll hit itself. And then there's also this many collisions thing here, right? Many collisions. I'm going to add a bunch of these, right? If I had a bunch of these, 30 of them, and add a bunch of these. Notice that the average energy here is below the energy well, but I am getting some reactions. I am getting some AB plus C, because even though the average energy is not high enough, there are some in that distribution that are higher. And if I do increase the temperature, if I raise the temperature and I raise the average energy, you'll see the reaction rate go faster and faster. It's still below that hump though, right? So they are still reacting and they're below that hump. And I can raise it even more. If I raise it past that point, you see lots and lots of reactions happening. So that's the concept of a distribution. You can have, I can reduce the energy here and we'll see it go back. Yeah, not a lot of reactions happening now. So yeah, that's a cool little applet that shows you reaction rates, and especially the importance of this Boltzman distribution. In the many reactions example, we had the average temperature way below what it would needed to react, and yet we still had reactions happening, just like the water evaporating at room temperature. Other things that can affect it is, if you have more stuff, you get more collisions, so you get a faster reaction rate. Surface area, more surface area means more space for collisions to occur, so you get more effective collisions. Effective collisions is really the important thing, right? It's the effectiveness of the collisions. More pressure or more concentration means more molecules, so there's more collisions. And then the catalysts. Catalysts are really interesting. Catalysts generally will just hold molecules in the right orientation, and then there's a higher chance of effective collision because they're already held in the right orientation. So catalysts, a good example of this would be when we hydrogenate. We have a platinum catalyst, and it's holding hydrogens in exactly the right distance apart so that the alkene can come in, and it's just the right distance that it attaches across the double bond. It's very, very cool. So yeah, that's a factor that affects reaction rate. All right, let's talk about energy. So I'm going to pause and set that up. So we're getting into the laws of thermodynamics, and this is where we have to talk about energy. Energy is very hard to explain what energy is. It is an abstract concept. Put an S in there, whatever, I'm going to leave it. But the change in energy can be measured. We can put numbers to a change in energy when something heats up or cools down when it does work. So energy is the ability to do work of some kind. So, if you take something and lift it, you're using energy. You're putting that energy into the thing that you've lifted, and then when it drops, it releases that energy and stuff like that. There's a bunch of different kinds: gravitational, elastic, chemical potential, electric potential, nuclear, magnetic, kinetic, right? Kinetic energy, which could be temperature. We're particularly interested in chemical potential energy, because it's kind of stored in bond potentials. It's stored in what kind of bonds you can make. We'll get into that in a couple of videos. We'll talk about bond energies. And thermal kinetic energy, because that's how chemical energy is usually released. So, if you burn something, you're changing the chemical bonds, and that changes the temperature, and it makes things jiggle a lot more because you're releasing that chemical potential as thermal kinetics. We're always going back and forth between thermal kinetic and chemical potential. Here are the laws of thermodynamics. Here are the simple terms of the laws of thermodynamics. They're not in order either. The first law is energy cannot be created or destroyed, and it only transformed into different forms. This is very important for us. We're going to assume perfect transformation, of chemical to thermal, thermal back to chemical. The second law is that it's almost impossible to be 100% efficient, that you always lose some energy as heat, as some kind of unusable form. We don't really care that much about this one in our branch of chemistry, at this intro to thermochemistry. Talking about heat loss is kind of annoying, so we're just going to assume 100% efficiency. Later, you'll talk about heat loss if you ever take analytical chemistry and thermochemistry and stuff like that in university. Then number 3 is the hotter things get, the more disordered they get. So solid is more ordered than a liquid, is more ordered than a gas. This is a concept called entropy. So there's a certain amount of energy that goes into making things more or less disordered. And it's a core principle of atomic theory, right? Hotter is more motion. And the summary here is that energy in has to equal energy out, and we have to assume 100% energy conversion between our thermal and our chemical potential. That's all we care about, thermal and chemical potential. That's all. So potential versus kinetic, right? We convert between potential and kinetic energy. Potential is part of the system, has to be transformed to be useful. In chemicals, it's stored in the bonds that we can possibly make. So, I've got some, I've got this styrofoam. Right? Styrofoam is flammable. Styrofoam's here. There's oxygen in the air. Right? There's oxygen in the air. If I combine that styrofoam with the oxygen in the air, I'm going to release kinetic energy. But I'm not doing it right now because the oxygen's not hitting hard enough. There's no effective collisions. But the energy is there. It's potential. There is potential to make energy because I've got the oxygen. It's all over the place. And I've got my styrofoam. I've got my thing. Or these matches, right? Matches, same thing, combined with oxygen, and you can release energy. It's not releasing energy right now, but the potential is there. Kinetic energy is the motion. It's useful right away. And the motion of these particles is useful right away. So there's thermal energy. The temperature of the system is the kinetic energy. It's often the thing that sets off a chemical reaction. So, with these matches, which I just opened upside down, shouldn't have done that. With these matches, I use friction to heat up the matches. And that friction, that kinetic energy from the friction sets off the reaction, gives us enough initial energy to make the fire. Wow, amazing. All right, so that's kinetic energy versus potential. Kind of a important concept. We will talk a lot about this stuff. Heat versus thermal energy. So this is heat. In physics, heat, in science in general, heat is the transfer of kinetic energy, is the transfer of thermal energy from something hotter to something colder. It's given the symbol Q. Don't know why it's Q. But yeah, heat is transfer of energy from something hotter to something colder. Technically, it's transfer of any energy. So that's heat. Heat is a transfer. You can also use heat as the amount of energy that gets transferred. So, when you're in the shower and you're in the hot water is warming you up. There is heat going from the hot water to you. There's a certain amount of heat because you heat up by a certain amount. That is what heat is. It's the transfer of the energy from high to low. Meanwhile, the energy itself is thermal energy. It's the total amount of jiggly motion of the system, right? So, for example, I have more thermal energy than my cat because I'm bigger. I have more particles. They're moving. There's more of them. There's more total movement. If I went into, say, a bathtub of cold water, I would heat up that cold water more than my cat would because there's just more of me. Therefore, I have more thermal energy. Heat would flow from me into the bathtub. So yeah, that's thermal energy. And then temperature is the average kinetic energy of the particles. I have relatively low temperature. Meanwhile, say a cup of hot water would have a relatively high temperature. So it would warm me up if I drank, say, a cup of hot tea, and I would feel nice and warm. So heat versus thermal energy versus temperature is an important concept. We're going to use heat transfer a lot, and we'll see heats of reaction and things like that. It's how much energy will get transferred into and out of a chemical reaction. That's what I mean when I say heat. So here's a great example of what we mean by heat in terms of a transfer, right? Heat is energy coming in and out of what we call a system. And a system is defined by us. We get to choose what the system is. I could maybe consider my human body a system, right? Matter can come in and out. Heat comes in and out. If I'm in a cold environment, I will heat up the environment. If I'm in a hot environment, the environment will heat me up. Really what's happening is both are happening at the same time, and one is just stronger than the other. And there's three types of systems. There's isolated systems, where there's no matter or heat that can get exchanged. The closed system is closed, so the matter can't get in and out, but the heat can. And open systems, matter and heat can both come in and out. So isolated systems don't really exist, but we can get kind of close, like a thermos. Planet Earth is a good example of a pretty much closed system where matter doesn't really come in and out of the planet, but energy does. We get energy from the sun. We radiate energy back out in terms of infrared rays and radio waves and stuff like that. And the human body is clearly an open system because matter can come in and out while I breathe and eat and drink and stuff, and heat can come in and out as well as I heat up my surroundings, as my surroundings heat me up, and stuff like that. Here's an example system, a burning candle. The candle is the chemical system. There is wax coming in and air coming in, and it is burning and exchanging energy with the surroundings. So there is wax coming in from the bottom, air coming in from the outside. The reaction is happening in the flame, and out goes energy, thermal energy. We're heating up the air, and carbon dioxide and water and all that kind of stuff. There's a really cool demo of this invented by Michael Faraday back in the 1800s. It's a very simple one. Here's a burning candle. He's going to take a piece of paper and put it over the candle. And look at where the paper gets black. In a ring. In a ring. So the heat, the actual energy, is released in a ring of the flame. Not the center, in a ring around the flame. Because the center is where the wax is coming out. Center is the wax coming off the wick. From the outside, there's air coming in. And so the ring of energy, of heat you see there, is where the fuel is meeting the oxygen, where the reaction is actually happening. So that's actually showing you that the reaction happens in this ring around the flame rather than in the center of the flame, which I always think is really, really cool. And that's where the energy gets released. This is where we get to endothermic and exothermic. The candle is exothermic because heat is flowing from the system to the surroundings. The chemicals are losing energy, the surroundings are gaining energy. So that's an exothermic system because heat is flowing to the surroundings. The opposite is endothermic. For example, an ice cube at room temperature. Liquid water is higher energy than solid water. A liquid is higher energy than solid. So thermal energy from the room is going into the ice cube as it melts. Thermal energy from the cube is going into the ice cube. This is endothermic. The ice cube is gaining energy. The room is losing energy. Remember, energy can't be created or destroyed. So making something colder is an endothermic process. The system is gaining energy. The chemicals are gaining energy. This leads us to defining these things and putting them into chemistry. So that's our next topic. So I'm going to pause for a second. We'll talk about thermochemical notation, which is how we define these things. How do we see it in a reaction? Well, we say heat, a change in energy, the energy going into or out of a system. Heat of whatever is the energy needed to accomplish the work, in or out. So usually this is joules per gram, or sometimes kilojoules per mole when we're talking about chemistry, because we like using moles in chemistry. So a joule is approximately the energy needed to lift 100 grams by 1 meter. So 100 grams is maybe the weight of a typical kind of like coffee cup is about 100 grams. Without coffee in it, just the cup itself is probably about 100 grams. And lift it up by 1 meter. That's 1 joule. Also the energy released when it drops a meter, if you want to think about it that way. So it's not a lot. It's not a lot of energy. And chemical and physical changes will have different heats. So here's an example. The heat of vaporization of water, 2,254 joules per gram of water. A gram of water is a milliliter of water, right? If you're vaporizing 1 gram of water, 2,254 joules. It's like lifting this thing 1 meter 2,000 times to vaporize 1 gram of water to turn it into a gas. If you're vaporizing a liter of water, which is a kilogram of water, do it 2 million times because a liter is 1,000 grams of water. Or 40.66 kilojoules per mole of water. So 40,000 joules per mole. The heat of combustion of TNT is 14,000 joules per gram. So 1 gram of TNT blowing up, 1 gram, it's a very small amount, will release 14,000 joules of energy, right? That means it could take this thing up 14,000 meters in a perfect world. Higher than Mount Everest kind of thing, right? You hit an airplane in flight with it in a perfect world with no air resistance and that kind of thing. So yeah, this is how we talk about energy in chemical reactions. We're not talking about the absolute energy of the chemical. We're talking about the change in energy based on whatever process we're interested in. So this one is combustion. The process of combustion releases 14,000 joules per gram of thing combusted. the process of vaporization requires 2,000 joules for a gram, or 40 kilojoules for a mole. So we're always talking about the energy change, the change of energy through the process. This is called enthalpy. Enthalpy is the total energy of the substance. We can't measure a total energy. It's very difficult. Right? If I take, say, this rock, right? It's got gravitational energy. It's above the earth. I can drop it to my hand. Now it's got less gravitational energy. I drop it lower down. It's got less and less and less. I'm on the second floor. It's still got energy even if it's on the floor, and so on. And then it's got energy relative to the sun. It's got nuclear energy. It's got chemical energy. It's got thermal energy because it's a certain temperature. There's a lot of energies in this rock. We can't really measure the total energy, but we can measure the change in energy. If I lift it from here to here, I have changed its gravitational energy, but really haven't changed anything else. So we can measure the change in energy. We can't really measure total energy. That's why there's always a delta. So delta H we can measure. And delta H happens to be equal to the heat. Heat is the change in enthalpy most of the time. We're not really going to get into entropy and stuff like that. So delta H is how we talk about energy changes in reactions. Here's how we do it. This is thermochemistry notation. Control-Shift-T. Right. It's usually expressed in kilojoules per mole, and because we use moles in chemical reactions, right? If I write this, you know that it's 1 mole of water and 1 mole of gas. So when I write 40.66 kilojoules, it's kilojoules for a mole of the reaction. And there's 2 ways to do it. One way is to put it into the reaction itself. So this is an endothermic reaction. It requires 40 kilojoules of energy to proceed. So when we require energy, we put it on the reactant side because the energy basically becomes a reactant in our reaction. We need this. And so we put it on this side. The other option is to have a delta H value outside of the reaction, right? So just write the reaction normally, and then on the outside is delta H. And here it's a positive number, right? The system gains energy. These chemicals are gaining energy, and so the delta H is positive. Energy is going into the system. So delta H is for the system. It's for the system. So the system gains energy. Here's an example of one where it releases energy. Sodium burning in chlorine will release 204 kilojoules of energy per mole of this reaction, which means per mole of chlorine gas, as written. For every 2 moles of sodium, it releases 204 kilojoules. Every 1 mole of chlorine gas, it releases 204 kilojoules. That's going to get important later. So here it's on the product side because we're making energy. We're making thermal energy. It's coming out. And that's why when we write it in delta H notation, it's a negative number because our system, the chemicals, are actually losing energy. The environment is gaining energy. It's going to heat up. So this minus tells me that the environment is going to heat up and the chemicals are going to lose energy. This tells me the environment is going to cool down. So endothermic reactions, they have a positive delta H, and exothermic reactions have a negative delta H. Negative delta H. Yeah, that's thermochemical notation. We'll do lots of practice problems with that in class. And the last piece is nuclear. For some reason this is in the curriculum, so I'm just going to talk about it briefly. I know nuclear reactions are covered in grade 11, so some of you might have seen this in grade 11 chemistry. It's also covered in physics, so if you take physics, you learn about nuclear reactions. They just want you to compare nuclear reactions to chemical reactions in terms of how much energy. So nuclear reactions have very high, what we call energy density, because they use a different force instead of electric force for chemical reactions. They're using the strong and weak nuclear forces, which are much, much, much stronger and can release a lot more energy. All right, so fission versus fusion. Fission is when a big nucleus breaks apart. Fusion is when small nuclei come together. Both can release energy. Fusion will release energy when small nuclei fuse. Fission will release energy when big nuclei break apart. Small nuclei fusing, big nuclei breaking apart. Typically when a small nucleus fuses, when 2 small nuclei fuse, or when a big nucleus breaks apart, the release of energy is very, very exothermic. Right? If you remember back when we talked about physical change was like maybe 2 million, was 2,000 joules per gram, and a chemical change was about 14,000 joules per gram. Nuclear reactor, like a fission reactor, 80 million joules per gram for uranium, per gram of uranium. So it's thousands of times stronger than a chemical reaction. And then fusion is even another level past that. It's 1 billion joules released. That's the minus, right? The minus means that the reaction is losing energy and putting it out into the world. We can then use that energy to make electricity and stuff like that, turning the thermal energy into electric energy. It's 1 billion joules per gram for hydrogen. This is why fusion power would be so cool. If we could fuse hydrogen artificially, we can get a lot of energy out for a very small amount of hydrogen. Yeah, and that's it. So really the major things here was understanding the Boltzman distribution. If you can explain to me why water evaporates at room temperature when it boils at 100 degrees, you know you've got a good handle on that. The laws of thermodynamics, this idea of energy can't be created or destroyed. The concept of heat versus thermal energy, the idea that heat is flowing from the system to the surroundings. You can have positive and negative heat based on whether the system loses energy or gains energy. And heat in chemistry is based on the system, based on the chemical system gaining or losing energy. And then energy notation in chemistry, the delta H version and the writing it into the reaction version. So you have to know how to use both of these notations. And we briefly talked about nuclear reactions. They have this high energy density. Energy density is an important concept. Yeah, that's it. We've got hopefully a good basis for our energy unit, and I'll see you guys in class. Thanks a lot.